Welcome to the video for tutorial 4. We will firstly be looking at exercises under section 1.3 in your textbook. We are looking at number 38. It says, if f of x equals the square root of x and g of x equals the cube root of 1 minus x, what are the domains of A, f's composition with g, and b, g's composition with f? So before we start, let me just write down the domains of f and g separately. So I'm just going to do this here. So f's domain is going to be all positive real numbers, right? Because we can't take the square root of a negative number. And g's domain is going to be what? Well, we are taking the cube root of 1 minus x in g. So that means that the domain will be all real numbers. Okay, let's now look at f's composition with g. So f's composition with g of x is f at g of x, which is f of the cube root of 1 minus x, and the function f is the square root. So now we have the square root of the cube root of 1 minus x. And this we can also just write as the sixth root of 1 minus x. So let's now find the domain. So the domain of f's composition with g is. So if we look at this step here, we know we can't take the square root of a negative number, right? Therefore, this cube root is going to have to give us a positive answer. So we know that the domain of f's composition with g is all x, given that the cube root of 1 minus x is greater than or equal to 0. But if the cube root of 1 minus x is greater than or equal to 0, that means that what we have inside of the cube root, the 1 minus x, has to be greater than or equal to 0. That means that x has to be less than or equal to 1. And we can write this as the interval from negative infinity up to 1, where 1 is included. Let's now look at b, where we have to find the domain of g's composition with f. So, g's composition with f at x is g of f of x. This means it's g of the square root of x, which is then the cube root of 1 minus the square root of x. So now we want to find the domain of this composite function. So firstly, we know that for x to be in the domain of this composition, x has to be in the domain of f, and then we know that f of x has to be in the domain of G. So let's just quickly write that down. So the domain of G's composition with f is all x, given that x is in the domain of f and f of x is in the domain of G. What did we say the domain of f was again? So the domain of f is from 0 up to infinity, and the domain of G is all real numbers. What does it mean for f of x to be in the domain of G? That simply means that the range of f of x has to be in the domain of G. So let's just make a note up here. What is the range of f? The range of f will be the same as the domain, from 0 to infinity, since the answer of the square root of a positive number will just give us a positive number. So let's go back to the domain of G's composition with f. We said x has to be in the domain of f. That means that x has to be in the interval from 0 to infinity. Then we said that f of x has to be in the domain of G, which we said means that the range of f of x has to be in the domain of G. And the range of f of x is also from 0 to infinity, which is indeed in the domain of G, which is all real numbers. So our answer here is going to be the interval from 0 to infinity. Next, we are looking at the exercises under section 1.5, and we are looking at number 11. It says, sketch the graph of the function below and use it to determine the values of a for which the limit when x approaches a of f of x exists. So we have the function that is defined as follows. F of x equals 1 plus x if x is less than 1. F of x equals x squared if x is between minus 1 and 1. Where minus 1 is included. And f of x equals 2 minus x if x is greater than or equal to 1. Okay, so firstly, let's just sketch the function. So y-axis, x-axis. I'm just going to make 2 points here at minus 1 and 1. And what I'm going to do as well is I'm just going to work out my function values at those 2 points. So for the first case, I'm going to have, I have y equals 1 plus x. So when x equals minus 1, we will have y equals 0 there. Then, in this case, we have y equals x squared. So when x equals minus 1, we have 1. And when x equals 1, we also have 1. Finally, we have the case where y equals 2 minus x. So let's now start drawing our functions. Firstly, 1 plus x. 1 plus x is simply a straight line. We know that it takes on the value of 0 at minus 1. And we know it has a y-intercept at 1. So the function looks something like this. However, we are only looking at the part of the function where x is less than 1, minus 1. So we will therefore only be looking at this part of the function and disregarding the rest. Now if we look at x squared, well, we know x squared is a parabola. We know that it has a y-intercept at 0, so its turning point is just on the x-axis. And we also know that it takes on the value 1 for both x equals minus 1 and x equals 1. So we have our parabola that looks like this. And then at 1, the y value of 1 is not included there. And at minus 1, the y value of 1 is included. Next, I now want to look at my last part of the function, which is 2 minus x. So 2 minus x is once again a straight line. And I forgot to complete this part earlier, but when x equals 1, we will have y equals 2 minus 1, which is 1. Therefore, we know that the function will look like this. It will take on the value of 1 when x equals 1, and then we know it has a negative slope, so it's going to look like this. The actual question is to determine the values of a for which the limit when x approaches a of f of x exists. Well, can you see that if we look at this graph, we can see that the limit exists for all a, except we have a problem when a equals minus 1. Why do we have a problem there? Well, our left and right limits are different when a equals minus 1. So our left limit will be 0, and our right limit will be 1. So our left and right limits do not equal each other, and therefore the limit does not exist when a equals minus 1. So the limit exists for all a except when a equals minus 1. Next, we are looking at number 32, and it says determine the infinite limit, the limit where x approaches 3 from the left of the square root of x over x minus 3 to the power of 5. So what we basically want to try and do here is we want to look at the square root of x and x minus 3 to the power of 5 separately, and we want to see what happens to them when we have x approaching 3 from the left. So if we look at our numerator first, we have the square root of x. X is approaching the value 3 from the left. So the square root of x will just be the square root of a number which is very, very close to 3. So that will give us a positive answer, right? So for our numerator, we're going to have a positive value. Then, if we look at our denominator, we have x minus 3 to the power of 5. So can you see that If x minus 3 to the power 5 is negative, that means that x minus 3 has to be negative. And if x minus 3 to the power 5 is positive, that means x minus 3 has to be positive. So we're just going to look at x minus 3. Let's just quickly draw the graph for the function x minus 3 down here. So it will look like this. It has a y-intercept at minus 3, and then it has an x-intercept at 3. So we now know that our x is approaching 3 from the left. But can you see that as x is approaching 3 from the left, all of the y values that this function takes on are negative y values. Therefore, x minus 3 takes on a negative value as x approaches 3 from the left. Therefore, x minus 3 to the power of 5 will also be a negative value. So, I'm just going to write here that the denominator approaches 0 from the negative side as x approaches 3 from the left. Therefore, we now have some positive number divided by a value that approaches 0 from the negative side. So the answer for our limit will therefore be negative infinity, because we have a positive number divided by a negative number infinitely close to the number 0. Next, we are looking at the infinite limit as x approaches pi over 2 from the right of 1 over x sec x. What I'm going to do here is I'm going to consider my two functions that I have a product of separately and see what happens with them. So I have 1 over x. Once again, if you wanted to, you could look at it as having a numerator, which would be sec x, and a denominator of x. That would also work perfectly fine. So let's look at 1 over x. Well, if x approaches pi over 2, which is a positive number, 1 over x will definitely also approach a positive number, so we know 1 over x will be positive. If we now look at sec x, so what is sec x again? Sec x is 1 over cos x, and we know that cos x looks like this. So this value here is pi over 2. So if x is approaching pi over 2 from the right, the y values taken on in this case will be these. So they will all be negative. And they are approaching 0. So cos x is approaching 0 from the negative side. So we have 1 divided by something that is approaching 0 from the negative side. So that would give us negative infinity. Therefore, we know sec x approaches negative infinity. So we have 1 over x multiplied by sec x. So we have something positive multiplied by negative infinity, which most definitely will give us negative infinity. Next, we are looking at the exercises under section 1.6, and the first one we're looking at is number 11. This is a really simple one. So we have the limit as x approaches 2 of x squared plus x minus 6 over x minus 2. So obviously we can't just plug in the number 2 directly into x's place here, because we'll have a problem in the denominator. We have a 0 there. But what can we do? We want to try and get rid of that denominator that gives us a problem. And we can do that quite easily in this case, simply by factorizing the numerator, so that we have x plus 3, x minus 2 over x minus 2. Those two factors cancel and we are left with the limit as x approaches 2 of x plus 3. And now we can just plug in our number 2. So we have 2 plus 3, which is 5. Next, we are looking at number 22. So we have the limit as u approaches 2 of the square root of 4u plus 1 minus 3 over u minus 2. Once again, we can most definitely not plug in the 2 immediately. And why is that again? Well, we would get a 0 in the denominator. So we definitely want to try and get rid of that u minus 2 in the denominator again. When you have a function of this form that you are working out the limit of, so you have a square root 4u plus 1 minus 3 somewhere in there or something of that form, a good idea to try and manipulate this limit is to multiply it by 1 in the form of 4u plus 1, and then instead of a minus, plus 3 over the square root of 4u plus 1 plus 3. So I'm simply multiplying by 1 in another form so that I can manipulate my limit a little bit. This is then equal to the limit as u approaches 2 of, so I'm going to multiply these top two factors, and I'm going to have the square root of 4u plus 1 squared minus 3 squared over u minus 2, and then the square root of 4u plus 1 plus 3. Let's simplify the numerator a bit. So the limit as u approaches 2, and then we have 4u plus 1 minus 9 over u minus 2 square root of 4u plus 1 plus 3. So can you now see that in the denominator, we only have one problem basically. We still have that u minus 2, and that's the thing we want to try and get rid of, because the square root of 4u plus 1 plus 3, if we plug in the u there, we don't have a problem because we don't get 0. So let's look at the numerator. The numerator now becomes 4u minus 8. And remember, my goal is to get rid of this u minus 2. So the 4u minus 8 I can write as 4u minus 2. And can you now see that now I can cancel out the bracket in the numerator and the denominator. So I have the limit as u approaches 2 of 4 multiplied by u minus 2 over u minus 2 multiplied by 4u plus 1 plus 3. These two brackets cancel, and now you can simply plug in the number 2, not going to do all of those steps, and you get your answers 2 over 3. Next, we are looking at number 63, and it says, show by example that the limit as x approaches a of the product of fx and gx may exist, but neither the limit as x approaches a of f of x nor the limit as x approaches a of g of x exists. So we want to find an example to prove that this is actually possible. A very simple example to illustrate this will be the following. So we say let f of x be equal to 0 if x is less than 0 and 1 if x is greater than or equal to 0. And then g of x is minus 1 if x is less than 0, and 0 if x is greater than or equal to 0. So clearly, in this case, the limit of f of x as x approaches 0 will not exist, because we basically have a jump in our function there. And similarly for g of x, the limit when x approaches 0 of g of x will also not exist, because we have a jump in our function. However, if we look at the product of f of x and g of x for all values of x, we get 0. So it's a constant function. And does the limit of a constant function exist? Most definitely. It's just the constant value. So let's write down everything we just said. We said that the limit as x approaches 0 of f of x and the limit as x approaches 0 of g of x do not exist. But the limit as x approaches 0 of the product of these two functions is just the limit as x approaches 0 of the constant value 0, which is 0. Therefore, we've proven by example that this is indeed possible. Okay, so just a few hints, lastly, for the principal exercises of the tutorial. So for number 6, you are given two equations and you are asked what's wrong with the first one and why the second one is correct. For the first one, the hint is to compare the domains of the left-hand side and right-hand side of the equation. And then for the second equation, when we find the limit as x approaches a of a function, do we actually ever consider x when it equals the value a? Then for number 7, refer back to your limit laws. What's the limit of the product of two functions equal to? How else can we write that? By using the limit laws. And then for number 9, also try and use your limit laws to find those limits that you are asked for. This is the end of this week's video.